Hey guys, this video is for Cal BC. This is from 6.3 and it's called Logistic Growth. So some things I want you to recall is that a rate of change has always been directly proportional to the amount, okay? So in Algebra 2 and in Pre-Cal, you might have learned that a slope or the rate of change was some value k times p. And then in calculus, you learn to do the antiderivative of that. But in pre-cal, you learn that you would find the amount, okay? Sometimes they use that as an a or a p, was equal to, remember this PERT equation, which was the initial amount or initial population, depending on what you're talking about, times e raised to r or k, two different variables used to represent a rate, times t, which is time, okay? When you learn that in Algebra 2 or Pre-Cal, we were talking about exponential functions, okay? So, for example, if we talked about money, we would talk about as time grew, as time passed, your money would grow, right? Or if we talked about a population, populations grow as time passed, okay? So, when we talk about that in the realm of math, this exponential function will grow forever. That's what that arrow means, that it goes on to infinity. But if we talk about reality, whether it be money or a population, imagine population, and we're talking about an island. The population cannot grow forever. It's impossible. You'll run out of resources, people won't fit on the island. So that's where logistics growth starts to change the image of an exponential graph, okay, in order to fit these realistic situations, okay? So we are going to rewrite a new set of equations for the rate and for the amount according to logistics growth, okay? And instead of our graph growing forever, our population, let's say we're talking about, is going to grow really fast. And then there's going to be a point where, let's say, too many people, it starts to get a little crowded on that island. Resources are going to start to run low, and now the population is going to grow at a slower rate, and there's going to become a point where we can't fit any more people, okay? So let's talk about that. I put an M on that asymptote there. That's going to be called my carrying capacity, okay? So reality says that I can pass a certain amount, and we're going to call that certain amount M, and again, that's going to come up very often called the carrying capacity, okay? So let's look at those two new equations now. Okay, K and M are going to be constants. Those are going to represent numbers. So the rate is going to be K, some number K times a variable P times 1 minus that variable P divided by M, where M, we said, is our carrying capacity. So if they give you the equation as a rate, we know that that number down there, as long as this is a 1, is my carrying capacity, okay? It's the maximum amount it can go to. If they give it to me set up as the amount, the carrying capacity M will be up here in the numerator. M divided by 1 plus A, the amount, times E raised to negative K times time, okay? So let me show you the difference between these two graphs. If we're talking about a population growing because, people start having families and multiplying, then the graph is going to go upward in between 0 and that carrying capacity. And my rate is going to be greater than 0. It's going to be positive, meaning I'm having growth, okay? If, let's say on that island, unfortunately at some point disease strikes, and now instead of growing, the population is starting to decrease, you're going to see that my function is above, it's greater than my carrying capacity, and it's going to start to decrease, okay? Which means that my rate would be less than 0, it'd be negative. So let's talk now a little bit about the behavior of this graph and what we can understand by its concavity, okay? We have said that when a function looks like this, it is increasing and concave up. We read that from left to right. So that means that whatever's happening, whether we're talking about a growth of a population, it is not only increasing, but it's increasing at an increasing rate. So it's growing fast, okay? Now, at this point where I change concavity, my point of inflection, it looks like this, which means I'm increasing, but because it's concave down, it is increasing at a decreasing rate. That means, yeah, the population is still growing, but it's starting to slow down, okay? That means that this point of inflection is where the population was growing its fastest, because it was, remember, increasing at an increasing rate, so it's growing fast, 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 and now, once it grew its fastest, it hit a point that it starts to grow, but it's starting to slow down its growth rate, okay? So now the big question is, where is that point of inflection? How do I find that point when the population was growing its fastest, okay? If we say that that point is the point of inflection, we can find that by doing the second derivative. So I have rewritten right here the rate equation that I gave you a moment ago. Make sure you have this one memorized and the amount equation memorized, okay? Both needed for the AP test. I took a moment and I distributed, in order to just use power rule, the K and the P, okay? So now, I'm going to rewrite it one more time. I'm going to say dP dt equals, K is going to be a number, P is my variable, minus, if P is the variable, I'm going to write K over M as the coefficient, and then P squared. So now when I go to do the derivative, this is the second derivative, which is where I find concavity and points of inflection. I'm going to do power rule, but remember that you're going to have to do this implicitly, okay? So remember, K is a number and P is the variable. That's like if I'm saying 5x, the derivative of that is just 5. So the derivative of Kp is just K, and then implicit, the variable becomes dP dt. Looks a lot like when we did related rates. Minus, remember, this is a number, this is a variable. So when I do power rule, it's 2 times the number up front. Subtract 1 from the exponent, it's just p to the first power. And then implicit times dp dt. Okay? Now, I noticed that there is a k and a dp dt in this first term. And in this second term, there's also a k and a dp dt. So I'm going to factor those out. Since I'm still talking about the second derivative, I'm just going to bring down my equal sign. Factor out that k dp dt. If I divide it out here, I get a 1. Minus, if I divide it out here, I get a 2 over m times p. Okay? Now, if I want to find points of inflection, I set that second derivative equal to 0. Okay? When I have two things set equal to 0 and they're separated by multiplication, I can set each of them equal to 0. Okay? So I'm going to say K dP dt equals 0. And so does 1 minus 2 over mp. Okay? For this right side, I'm going to move the 1, or actually I'll move this over so that it goes positive, and I say 1 equals 2 over mp. And if I want to isolate p, then I'm going to divide by this fraction, which is a keep, change, flip. I'm going to multiply by its reciprocal to the other side. Okay, so the first point of inflection that I get, let me move that down a little bit. If P stands for the population and M is for the maximum capacity, that means that my point of inflection for the population is when I'm half of the maximum capacity. So now I can go back in and say that this happens here at half of the maximum capacity. So if they tell you that the max capacity, if it comes out in the equation, let's say it's 1,000, then that point of inflection when I was growing fastest is at half of that, okay? Now, if you catch that, you don't have to clean the rest. If you do clean the rest, you would be plugging in what dP dt is right in here, solving each, okay? And you would end up getting 0 and m as your other answers, which should make sense that at 0 is one of them, and up here at m is the other because it's my start of being concave up, then it's my change, and then I end being concave down once I hit M, okay? So have this memorized, guys, that half of the half of the maximum amount, the carrying capacity, is going to be where my point of inflection is, which is where my population is going to be growing fastest. Taking a look at this example, it says the growth rate of a population P of bears is modeled by the differential equation dp dt. Here's your equation, where T is measured in years. Question A says, what is the carrying capacity for bears in this wildlife preserve? Meaning, what is the most amount of bears we can have, okay? So for starters, let's remember that my dp dt, right, my population equation should read Kp times 1 minus P over M. So the first goal that I have here is trying to get this equation that they gave me, right, to look like this one. Your easiest way to do that is to get this 100 to read a 1. That's your goal. Now, I do that by dividing out this 100. I'm going to factor it out, okay? So if originally dp dt, I had this equation, I'm going to take out the 100 up front. So I'm going to say 100 times that 0.008p. I factored it out. So 100 divided by 100 is going to be 1 minus p divided by that 100 that I took out is p over 100. Okay, so if you were to distribute this 100 back in, you'd see that you'd get right back to your original question. So just to clean that one more time, you could probably already start seeing your answer. 100 times 0.008 moves my decimal 2 times over, so I have 0.8 p times 1 minus p over 100. And now that it's clean, you can see what your k is, right? P1 minus p over, and you can see what your m is. But since they asked for carrying capacity is my m. So my answer here is that 100, and we're talking about bears, is my carrying capacity, okay? Let's go ahead and look at the next one. What is the bear population when the population is growing fastest? Keyword there is growing fastest. And we know that we are growing fastest. We said that equation was going to be my carrying capacity divided by 2, which means I'm doing 100 divided by 2. So that means it's going to be at 50 bears. That is when the growth rate of the bears in the preserve was growing fastest. All right, so you can see these questions aren't too hard. It's just really the vocabulary and the concept that you have to get down pat. Okay, let's look at one more part. What is the rate of change of the population? So here's the question. What is my rate of change? So what is my dp dt of the population when, so they're giving you your variable there, it is growing fastest, okay? So right here, they just told me growing fastest is my when. So they're telling you is when P, my population, is 50, what is the rate of change? So what is that dp dt? This is what they're really asking, okay? So again, the interpretation of the question is the hardest part. So now you just plug that in. In our first question, we had cleaned out my dp dt. You can use that one, or you can use the original one that they gave you. Either one works, okay? So we'll say that dp dt when p is 50 is going to give me 0.8, P is 50, times 1 minus, again, P is 50 over 100. Okay, so this is going to give me, it's going to give me a decimal, but remember, since we're talking about bears, we can't talk about a portion of a bear. So you can say that it is approximately, when you plug that in, 20 bears. And because this is a rate, we need 2 units. They told us that time is going to be in years, so this is roughly 20 bears per year. All right.